So we have discussed the op-amp biasing yesterday, op-amp design, high gain, cascade output stage, etc. So a couple of things that were left was, say, common drain buffer. So somebody had rightly asked that if you want to have very low impedance, what kind of buffering, what kind of circuit we need to have. Uh, so I think I'll have to go to the previous section and bring that circuit, which I had kept it. So we'll discuss a bit about buffering. So I'm not drawing the biasing circuit for this stage, already discussed. We'll directly go to the buffering. In the biasing circuit also there is some improvement possible. So maybe we can discuss that. So uh, reduced swing cascade can be used for an improved biasing. Let us discuss that because here you're using cascade stages. So a better strategy for biasing the cascade stages. This is the pen, right? Reduced swing cascade mirror. Here the way we have biased it, especially the upper devices, the way we have biased it, if you remember, we are bringing a current, whatever, VB is coming, we are bringing that current over here, VB, and they are mirroring it upside, and then we are having two PMOS transistors like this. And then we are also mirroring it into another NMOS branch, and then using NMOS transistors like this. I had slightly modified the circuit given to you, but in the theory class, I had discussed this scheme that this can be used for biasing the VBP, VBP, and this can be used to bias the VBN. Almost same voltage, so VBN. So these are in case you are using this scenario, it will be slightly different. It can be slightly different, but eventually they will be pretty close, VBN and VBP, and then you are trying to wait. Then you are trying to generate the bias voltage for NMOS and PMOS. Now, if you look at this condition, what is going to be the swing? So what is happening? So what is going to be the swing, voltage swing at the output? How is it going to be limited? So what is the V out min that we can have in this scenario? What will decide the V out min? Yes, anybody? What will decide the V out min? This is the V out. This is your V out. So V out min will be decided by what?
VPN.
Sorry, VP. Yeah, VBN minus VT, right? So gate voltage minus VT. So the minimum voltage that you can have is VBN minus VT. And V out max. The VBP that will be decided by VBP. VBP plus mod VT. Mod VTP, whatever you call it. This is your VT. Yeah. This should be clear, right? So gate voltage is which is VG, VBN. The output can go minimum to VBN minus VT. And output side, upper side, it can go to the gate voltage of PMOS plus mod VTP. I don't get too many answers. Very few people actually answer. So I hope these things are clear. And otherwise, I'm just going on progressing step by step. And if majority of people are not clear about basic things, then it will be a problem. So now In this scenario, ultimately the swing will depend upon VBN and VBP. What is the minimum value of VBN that we can have and minimum value of VBP we can have? So eventually the swing will depend upon VBN and VBP. So we need to minimize the VBN and we need to maximize the VBP minimum, and we need to see what is the max VBP possible. So if you look at VBN, for example, similar whatever we do for the NMOS side, similar thing will be applicable to the PMOS side. So for the NMOS side, what is the VBN? What is the VBN dependent upon? Yes, quickly. VBN is dependent upon what?
So not of the PMOS above.
Sorry, VBN is dependent upon?
The R naught of the PMOS above. Like if its R naught is very high, it can like generate a high potential drop across it without changing the current much.
R naught. Where is R naught coming into picture?
Like if we are using a current mirror, then the R naught of the PMOS above, which is used for mirroring, is very high. It can like act close to a current source.
So
We can ensure that most of the potential drop is across it, so the VBN can be reduced.
no, that is not the case. VBN is not dependent upon R naught. Sorry.
Will depend on the W by L ratio of the this MOS, that is
Yes. So
for
whatever the
given
MOSFET charge, so if you call this, whatever, you can call it M9, M10 or whatever, M9, M10. So ultimately, the net bias current is fixed. So whatever bias current we are having, suppose IB by 2, we are getting the same IB by 2 here. And for that IB by 2, ultimately the VBN will be 2 VGS. So VBN in this case is equal to 2 VGS. Assuming that the M9 and M8 and M9 are identical, so it is going to be 2 VGS of this transistor. And here we are also basically constrained with the W by L ratio. Ideally, you have to just reduce the VBN. We will just go for increasing W by L of M9 and M8. So you can say that, okay, just increase the W by L of M9 and M8 and you will get lesser VBN. Is that okay? Is it fine? What is the problem? Yes. Can I simply increase the W by L of M9 and M8 and make the VBN lower? Because VBN is dependent upon VGS, right? So it is 2 VT plus 2 V over drive. V over drive. How can you increase the, how can you reduce the V over drive? By increasing the W by L of M9 and M8. So still, if you are able to reduce it further, you will minimum at least get 2 VT. So VT is a significant number, maybe 0.35 volt or something like that. So 2 VT is a significant value, significantly high value. So 0.7 volt, 0.6 volt, 0.7 volt. So if you're looking at a VDD of 1.2 volt, and out of that, your 0.6 volt is going just like this, it will not be very, it will not give you a good swing, right? So if the VT is in advanced scale nodes, the VT may be relatively low. So in this case, I guess for 32 nanometer, the VT may be around 250, 300 millivolt. So if the 2 VT is going just like that, then whatever V overdrive is there, despite that, you will not get much margin. So the VBN will be basically close to 2 VGS. That is at least 2 VT. At least 2 VT means at least say 0.6 volt. Then 0.6 volt minus VTN 0.3 volt. So, and then the overdrive voltage is also non-zero. So only way to reduce the overdrive voltage is to increase W by L of M9 and M8. Is that okay? Is that acceptable to just increase the M9 and M8 W by 8 and then bias the VBN with that? What is the problem?
So we will also have to increase the W by L of the MOSFET where we are mirroring the current.
Yeah, so you're mirroring this, to the, if you call it, say, the numbering, I have missed it, but let me call this M10, M11, M12, whatever. So in this case, whatever size of M11 is there, if the ratio is not maintained and your M9 is increasing and M11 is same, then the, first of all, the bias current in this one, the DC current is decided by these two branches, the M6 and M9, M10, because ultimately the VGS of the M10 and VSG of the M6 is being fixed by the previous stage. So the DC bias current is decided by this, but now you are lowering the VBN by just increasing the M9 dimension. So as a result, now the VGS of the M11 that is dependent upon W by L of M11 and the your overall current. Overall current, we are trying to keep it same as say IB by 2 because the current in this will be decided by the mirroring ratio between these transistors, mirroring ratio between these transistors. That is anyway IB by 2. But now we are forcing the gate voltage of VBN to go down. Therefore, the VGS will remain same. The source voltage will go down, and then this transistor will enter into triode region, right? So we can't arbitrarily make the M9 large so that we can get a lower gate voltage because that will, push the M10 into triode. And second thing is that your in order to mitigate this, what you have to do, you have to increase the W by L of M11 also. So in that case, if you're just increasing the W by L of M11, if you are reducing the L or if you're increasing the W, that will basically slow down the circuit because you are additionally adding some parasitic capacitors. And along with that, the bias current is anyway fixed. So when lambda ID is remaining relatively fixed. So you have to basically increase the W by L of these. So one possibility is that you go on increasing the W by L of these two devices. You also correspondingly increase the W by L of M9 and M8. That will reduce the overdrive voltage, and then you are left with the 2VT. So effectively, if you are left with 2VT, then what is the Vout mean that you will get? The Vout mean will approximately become equal to 2VT minus VT. So suppose you are able to increase the M9 and M8 significantly, very large value, you are keeping 100 micro or something. Along with that, you also increase the VBN value. Now, the VBN value has been increased, and as a result, the VGS is reduced, and the drain voltage is still sufficient. But again, for the lowermost transistor, remember the gate voltage is determined by the guy here, and if you try to push the source voltage of this towards lower value, this M10 is going to enter into triode. So VD10 min will be divided by whatever VG10 minus VT. And you can't push the source voltage of M11 below that. So that is going to constrain how low you can make the VBN. So definitely this, it is a significant overhead, significant voltage headroom that these two stack MOSFETs are taking. So an alternate way of connecting the current mirrors I'm going to show you is this, which is called reduced swing topology. So rather than connecting the two MOSFETs directly in direct connected format, we use a slightly modified connection. So I'm drawing only the second branch. You have this NMOS. You have another NMOS. You put a R over here. This gate you connect it here. And this gate you connect it here. And then use this one to bias the two transistors. So this is the output stage transistor. I'm not drawing the entire output stage. You have the PMOS also likewise. Now, in this case, you are having IB by 2 over here. Now, for this IB by 2, suppose I name it as M8, M9. So this is 8, this is 9, whatever, 11, 12, whatever. So now, in this case, what is the gate voltage here? Minimum gate voltage here. This is your VGS8. So this is VGS8. And minimum voltage that you can have at this point is going to be VGS, VG8, you can call it VG8 minus VT. And the VG9 is going to be VG9 is going to be VG8 minus VT plus VGS9, because whatever is the VGS of 9, that is the gate voltage of M9. Therefore, the gate voltage of this is also the gate voltage of M12. Therefore, now in this case, what is the output minimum possible? V out min. V out min in this case will be this VG9 minus VT, which is something like VG8 minus VT plus VGS9 minus VT. So this is something like the overdrive voltage, VGS minus VT, VGS minus VT, right? So this is something like 2 V overdrive. So V out min, as compared to the earlier case, we are seeing that it is becoming 2 V overdrive. Now, the V overdrive, as we have seen, that you can definitely reduce by increasing the sizes. But even as such, the V overdrive voltage may be around 100 millivolt. So 2 V overdrive around 200 millivolt. As compared to the 2 VT term that we were getting earlier, now it is reduced to 2 V overdrive. So the output voltage can go all the way down to 2 V overdrive, which is going to be relatively small as compared to 2 VT. So earlier minimum value that we were able to obtain was something like VT, because 2 VT is the gate voltage, 2 VT minus VT. So that is again 300, 400, something like that millivolt. Whereas here it is 2 V overdrive. So this can be around 200 millivolt. So we will be able to pull the output significantly downward. We will be able to have lower, we will be able to allow lower output voltage. Condition for this is that you have VGS 8 and there is a relationship between the VG9 and the VGS 8. You have to size the R properly. So what should be the R value? So whatever IB by 2 we have, this IB by 2, whatever current is flowing through that, this into R should be equal to what? This should be equal to VG8 minus VG9, right? Because ultimately this node is VG8 and this node is VG9. So the VG8 minus VG9 should be equal to IB by 2 into R. So IB can be accordingly found out. So this is VG9 minus VG8. And
Sir, it should also be less than equal to VTH, right?
sorry,
Sir, it should also be less than equal to VTH, right?
less than equal to VTH means what? What should be less than VTH?
This product IV by 2 into R, because sir, like this point which is VG9 and VG8, that is basically the drain of 9, right? So that's VD9. So for MOSFET in saturation, I know that VD9 should be greater than equal to VG9
Yeah,
minus
that
of
constraint is
VD.
there, but here if you just look at the in terms of the gate voltage, this is the relation, right? So for gate voltages are decided by the sizes of this. So here in this case, we are trying to push it to the minimum value. For the minimum value, we have already seen that the drain voltage we are keeping at VG8 minus VT. So the condition is that we are trying to bias it for the minimum possible gate voltage. And for that, we are assuming that the drain voltage of M8 is at VG8 minus VT. And your drain voltage of M9 is also, we are trying to push it at the minimum value. So we are trying to already, this is the worst case scenario where we are trying to push it to the minimum value. So for higher output voltages, anyway, it will be okay because we are considering the worst case scenario. So
Yes.
here, the output voltage with respect to that, here we are trying to bias it such that the gate voltage of this the minimum for the minimum gate voltage for which M9 and M8 will be working in saturation region, you are having the M12 and M11 gate voltages biased with the same voltages, allowing the minimum possible V out min. If your output voltage is if the output voltage is in this case, it can on the upper side, the same effect will be given by the two PMOS. So the PMOS also similar scheme can be obtained. So for PMOS, what will you do? So whatever we have seen earlier, so similar thing will come. You have a bias, you have a PMOS like this, two PMOSs coming, you have a R over here, and you call this RP, you can call it RN. Now the same thing you do, you connect it like this, and then you connect it like this, and then you have the similar biasing for these two guys. So once again, here the upper side, you will have the similar 2V overdrive minimum voltage. So VDD minus 2V overdrive. This is VDD. This max, in this case, the out max value that you can have, V out max, will be VDD minus 2V overdrive of P. So that means this voltage minimum that you can have will be 2V overdrive, provided it is biased with this condition that you're trying to ensure that the gate voltages are the minimum possible value. So if you look at the VG9, VG8, what is it? So VG8 is like something like VGS. So VG8 is VGS, right? VGS8, and VG9 is something like VGS9 plus the VD8, right? So VD8 is something like the VG9 is something like VGS9 plus the drain voltage of M8, with the minimum value for this is VGS8 minus VT. So this is something like VGS, VG8 minus VT, and this plus VGS8. So this is something like V overdrive. So VG8 to VG8 minus VT and another VGS9. So if I look at the overdrive voltage in terms of the overdrive voltage, so we are going to get an overdrive term. Wait a minute. So VG9 minus VG8, right? So there's VG9 and VG8. So if I look at the minimum condition, we have seen that your VG8, the VG9 minimum case, VG9 is going to be equal to VG8 minus VT plus VGS9. This is the minimum value of VG9. And then we are having the VG8 over here. So this, the difference across the VRN is something like VGS9 minus VT, because VG8 will cancel out. So this is something like overdrive voltage, V overdrive of the M9. So in other words, the RN has to be sized such that the voltage drop across this is something like V overdrive of the M9. So, and that again depends on the W by L of M9. So here we are assuming that in our design, the W by L of M9 and M12, likewise M8 and M11 are same. And that gives us the overdrive voltage of M9. So corresponding to that overdrive voltage, approximately we can set that the overdrive voltage divided by R should be the I bias. So we should have overdrive voltage of 9 by the R should be equal to I bias. In this case, you are assuming I bias by 2. So I bias by 2, whatever is the current flowing in that branch. So again, the parameters will vary across process. There will be variations. So it is not easy to ensure that it is going to hold true for all conditions. Across process temperature, etc., it can vary slightly. But approximately in simulation, we can set it like this, that whatever is the R value, how do you decide that? Overdrive voltage of 9 divided by the current flowing in the M9. And that overdrive voltage, again, it depends upon the W by L ratio of M9. So in the simulation, if you see that, okay, for this much current, how much is the VGS coming? From there, you can know the overdrive voltage because the VT is known. And from there, we can have a rough estimate of R. And as I told you, it will not be exact under different conditions because of variations, etc. It may vary, but we try to approximately estimate the R with this method, and we have to make sure that under all process corners, the M8 and M9 are not entering into triode. So we can simulate for all corners and make sure that R is such that M8 and M9 are not entering into triode for the worst case scenarios. So in the 32 nanometer PTM, are you able to simulate for different corners? Do they have the model for different corners? So slow, fast, fast?
No, sir. No, sir. 32 nanometer does not. In PTM 32 nanometer does not have that one.
Okay. So for the time being, you can just simulate it for the nominal corner, the typical corner that we have. But eventually, this is going to help you in getting a higher swing, because both on the upper side, lower side, you are able to increase the swing. You are able to reduce the V out min, and you are able to increase the V out max. Is that clear? Anybody having any problem with this? So this is more common because otherwise your voltage swing will be poorer at the output. The first mechanism that we have seen, there you are having VT but plus 2V overdrive as the gate voltage VBN, which definitely leads to poorer swing at the output. So if you want to improve your swing, you can test with this particular scheme, and you will see that the if you are working with the common mode, sorry, if you're working in a say voltage follower configuration, you will see that the range will be extended for which it is working. Or even the distortion analysis that you're doing, you will be able to see that it will be able to operate for higher peak-to-peak swing output voltage without distortion. Any question before we proceed further? So this is called reduced swing cascade. This mechanism is called reduced. Why do we call reduced swing? It is improving the swing, but the cascade mirror itself is reduced swing because it can handle lower voltages at the drain. So for it, the swing is reduced, or I would say the voltage headroom required to operate the cascade is reduced. So some of the popular name for this is reduced swing cascade. There are some other ways also. In advanced node, there are some other ways of biasing, but for the time being, you can stick to this one. Okay. Another thing is the buffering part. That in cases where we need very low impedance for the output, how do we proceed? How do we go for the buffering? So let us try that. So what kind of buffers you have studied? I think for buffering, you have studied certain schemes in your course. What is the common buffering circuit? Yes, anybody? What is the common buffering circuit that you people have studied?
Sir,
Sorry? Yes, so there are single stage amplifier that you have studied. So do you remember anything which out of the single stage amplifier, which one can be can act as a buffer?
The source follower
common drain amplifier.
Yes, common drain. Why it can work as an amplifier? Buffer.
Sir, because it has a unity gain and has an extremely high input impedance, but a low output impedance.
Yes, so for a buffer, we would like to have very low output impedance, and for a unity gain circuit or unity gain stage, we would like to, first of all, whatever we add to this amplifier, we would like to make sure that it does not degrade the gain too much. So whatever buffer we are adding, it should not degrade the gain too much. Neither it should degrade the bandwidth too much. So bandwidth, why do we buffer? So there are two reasons for buffering. So first reason is, so can you tell me what are the reasons for buffering? Why under what conditions we will be needing buffering?
Sir, we will be using op-amps in the feedback, right? So the feedback may lower the output impedance which is being offered. So in order to increase that, we can use the buffer so that it follows as a like how when seen from the input output side as a high output impedance.
Okay, so somebody mentioned that anyway. So we have yesterday we had seen that the resistive feedback. If you use resistive feedback, it can have some loading effect on the output resistance, the overall output impedance. That is a good point. So because if you look at the feedback resistance, if you are using feedbacks, you know, between output and the negative input like this, and then you are for the resistive feedback scenario, if you consider the loading effect, it will you need to basically break this R. So you know how to basically get the loading effect for the feedback. You have studied this in your feedback topologies. For example, if I have to get the equivalent loading effect of this feedback resistor, how will you get it in this circuit? Yes, have you studied the loading effect of feedback network? Especially the person who answered, I thought, have you
Sir,
studied this?
it was not taught in the class, but as far as I can remember, I think this is the voltage feedback. I think voltage feedback. So we need to open the loop uh, and then let
No,
me
this is not a
forward.
voltage feedback. This is voltage sensing, but it is a current feedback. Why it is a current feedback? Those topologies you should have have you studied those feedback topologies? One is the block diagram study, and second is actual circuit implementation study. So in this
I have
case,
studied the block diagram, so it is I'm not much comfortable with the circuit. So studied the block diagram.
okay, so if I start going deep into the theory of feedback, it will take a lot of time, but very quickly I can understand, I can explain why this is a voltage sensing current feedback mechanism. So for a current feedback, what is the condition? So for the current feedback, the feedback connection can be in the same terminal as the input, right? So here the feedback connection is on the same terminal as the input. It is a shunt connection. So I can always, whatever is your voltage source over here, I can convert this voltage source and this, R into an equivalent Thevenin current source. So this I can convert it into an equivalent Thevenin source, forget about this. And then I can, consider the current input coming from here. And then I can treat this as a current to voltage amplifier. Because here in the negative feedback amplifier, the connection at the input is shunt. It is feeding back the input in the same terminal. Sorry, it is feeding back the output in the same terminal as the input. Therefore, there is a shunt connection at the input. And output also it is a shunt connection. Why? Because it is sensing the output. So if you short the output, the feedback will be destroyed, right? So there is at the output, it is sensing the voltage directly and converting it into a current. This is an AC ground. So based on the output, you are getting a feedback current, and then that current is going to subtract from the input. So it is a voltage sensing current feedback. And then in order to open the feedback over here, if you have to do the open loop analysis and you have to get the loading effect, the way it is done is that on the other side, if you have shunt feedback while opening, you will put the R over here and this RF will come here, RF will come here because other side it is shunt. So while opening the loop from the output side, looking at the output side, it will be grounded. Likewise, for this terminal, if you have to get the loading effect of the R at the input terminal, once again, looking at the input from this side, you are seeing other side is shunted. So here also you will have to put the RF like this. So this is generally, there are certain basic steps for opening the loop and considering the loading effect. So that if you have not studied, don't worry right now. But ultimately in the shunt feedback, this is like shunt feedback. So in shunt feedback, effectively this RF that is coming from output to the input, you will have an effective loading effect of the RF. So that is also another reason why we avoid using resistive feedback, because resistive feedback you will have loading effect and that will going to reduce your overall small signal gain. And one thing was the DC biasing becomes more complicated, but the loading effect is also another issue. So, but I know that you people have not covered actual resistive feedbacks and their open loop analysis and the loading effect incorporation. So if time permits, maybe in one of the classes we will go into some more detail and try to consider some examples, single stage amplifier as well as multi-stage amplifier, how to open the loop and conceptually analyze the open loop circuit for any given feedback amplifier. Right now, just at a high level, you understand that we are using a RF as a shunt feedback, and for opening the loop, we will have to basically consider the loading effect by opening RF from this point to ground and input side also RF to ground. And then if the RF is definitely in this case, GMRO square is a large impedance and RF is going to be relatively small. As a result, it can affect the gain. So this is something, the open loop gain, if it gets affected, what will be the effect? Even if it is still significant, even if it is, but as compared to the original open loop gain, it can be significantly lower because the GMRO square may be maybe very high, several hundreds kilo ohm. But now you are replacing it with RF, which is maybe just lower than that, significantly lower than that. As a result, the net open loop gain will go down. If the open loop gain goes down, what will be the effect? On the closed loop, your precision of the gain will go down. So that is one reason. That is another reason of avoiding resistive feedback. So anything else apart from the loading effect? Anything else? So if you put a buffer over here, so the question was, if you put a buffer over here in between. So if you put a buffer, like this is a common drain stage or buffer stage, its output impedance itself is very low, and as a result, you are not going to affect the loop gain because now, even if this buffer stage, this triangle buffer stage, if this gets loaded with a relatively smaller RF, it will not affect the gain of this buffer stage because the buffer stage has low output impedance. Is that clear? Whatever he said just now.
Yes.
Yes.
What else? So something related to this, there is another. First is the loading effect of feedback network. Is reduced. Is reduced. What else? What else? Yes, anybody else? Why do we need to buffer? You have studied all this, right? So already partially one answer is given. So the other answers are also related to this only. Yes. Anybody else?
So to separate two stages,
Sorry,
to separate two stages,
separate two stages. So why do you need to separate two stages?
like sir, if I directly connect this to another stage, it may the effective resistance seen by this may load the second stage.
Impedance seen by this may load the second stage.
If the impedance as the second stage sees for this may load the second stage, right?
I don't know what are you saying. Impedance seen by this at the second stage may load the second stage. Can you speak a little clearly? There are two cases. One case is you have a large capacitive load. That means the load capacitance is too high. You're having a CL which is very big. In that case, if you drive it directly using the output stage, it will kill the bandwidth further. Is that clear?
Yes, sir.
Then in order to prevent that, you may add a buffer stage because the buffer stage has So that will be able to drive a bigger cap. And second case is a small resistive load. If the load resistance of the circuit here, the loading effect, just like you are considering for the feedback, the actual load faced by the amplifier is also having a low resistance, low impedance. That will also kill the gain. So for both case scenarios, we need to use buffer. And this basically will help you in retaining the bandwidth, and it will be able to overall closed loop operation will be able to perform at higher speed. So these are the two basic things. So first case is large load capacitance. Second case is small load resistance. Both cases, this output stage cannot drive it. So for that, we need a buffer stage. And the loading effect of the feedback is also ultimately linked to that. So ultimately, if you're using a resistive feedback, then this problem will come, that the effective loading effect will also reduce the open loop gain. So now common drain, let us try to apply the common drain. So the question is, how do we? I'm not showing biasing circuitry for these middle two people, middle two PMOS and NMOS. So for the common drain, the question is, how do we approach? So you have two possibilities: an NMOS input device, a PMOS input device. The common drain can be two types, right? So you can have a common drain with NMOS input device, apply the input over here, and this can be the V bias. And another possibility is you can have a PMOS input device. And this is your input V in, and you apply this one as V bias, VVP, VVN. So which one we can use? Yes, anybody?
So it will depend on the common mode of the signal we are applying.
Sorry,
Sir, it may depend on the common mode of the signal that we are applying to the.
common mode of the signal. So suppose the question is that for both these cases, uh, what is the pros and cons? So only NMOS if I apply, then what is going to happen? Only PMOS if I apply, what is going to happen? So in the case of only NMOS, what is the problem? So the input, the input signal over here, it is output of this V out. V out, we are expecting, say, VDD minus V overdrive, 2 times V overdrive. Sorry, yes. So for the P side, it is V overdrive P, and it can go minimum to 2 times V overdrive of N. So if I assume VDD 1.2 volt, 1.2 volt minus say 100 millivolt is the V overdrive. So maybe it can go from 1 volt all the way to 2 times V overdrive, maybe 0.2 volt. So the range that we are seeing here, it is 1 volt to 0.2 volt, something like that. So now, if you have this kind of range of the signal possible at the output, what is the problem with only NMOS input stage? Yes, hello.
So
Quickly, Nandita.
if we have only the NMOS at the output stage, then if this is the voltage we apply at the gate, then I know that the drain voltage of the NMOS should be greater than equal to VG minus of VT, right? So if the gate is pretty high, then it may push the drain voltage of the NMOS quite high, and which may lead this PMOS which is above it going into the triode region.
Anybody else? Yes, quickly. These are basic things that I've already given you the signal range. The output of the uh, second stage is something like this, 0.2 volt to 1 volt. So with only NMOS input stage, what is the problem? I don't know. What are the people sleeping or what?
Now, sir, for
Sir,
values
for
of
very
0.2 volt,
low input,
Sorry?
sir, for very
sir,
low input, it may be turned off.
I don't know. Means, can you speak a little clearly? What is your thinking?
Sir, for NMOS to turn on, VGS should be greater than VT. So for very low input, NMOS will be turned off.
Yes. So when your input voltage is going towards a lower value, it will be turned off because your NMOS will require some VGS, right? So this VGS plus VO drive of the VDS of the B NMOS 2. So if this is 1, 2, 3, 4. So this NMOS stage, it will turn off for output voltages which are less than VGS plus VDS, VGS of 1 and VDS of 2. So for V out less than this, output will be clipped. Likewise, for only PMOS, what is the problem? For only PMOS, as we go towards, because input is applied here. So only PMOS, as we go towards higher value, it will be turning off likewise, right? So either only PMOS or only NMOS will not serve the purpose. So we need to combine both of them. So how do we combine? So one of the ways that people use is that you feed the output of these two stages. So both of them will be driven by, so the NMOS stage will be driven by the output like this. There will be a PMOS stage will be driven by, again, the output in a similar manner. This will be biased. And now the output of this and this will be driving the third stage, which is going to basically be the final output. So now this will be a third stage. Something like, sorry. So here, I can call this, say, this will be biased using some current mirror once again. So you can have the same current mirror producing some whatever VB you have. So you can have a current mirror which is producing these two bias voltages. That's this can go to this one, and you can also likewise generate the bias of PMOS and feed it here. So this will be say VG N, VG P. So this will be VG N. This is VG P. You can decide how much bias current you want to put. So the bias current to be put depends upon how much low impedance you want to have, because larger is the bias current, the smaller will be the impedance, and ultimately that will also decide the impedance of the output stage. So here, what is the role of the output stage in this scenario? So if you look at this, when the input is going too low, if the input is going too low, what will happen? the NMOS will be turning off, but in that case, the PMOS will be active. So the PMOS for very low input, it will shift it up. So suppose the input is coming around 0.3 volt. So this will shift it to the VGS plus 0.3 volt. That VGS may be 0.3 plus something like plus 0.3 volt. So this it will shift it up. And now this voltage is relatively high, right? It has been shifted by the PMOS common drain. NMOS side, if you see in that case, it is off. When the input was low, NMOS is off. As a result, this voltage will be completely down. It will be towards lower value. This will be, as a result, it will be NMOS is turning off, and this is coming at a very low value. This will be turning on the device over here. So now in this case, if this voltage has been shifted up, the NMOS is providing, this is completely low and the PMOS is turned on. So this is acting like a current source is turned on. But what is the role of NMOS here? This shifted up voltage, it will try to bring it down, because again, this provided a VSG, VSG drop, and then this NMOS is trying to bring it down further towards the source. Likewise, if you look at the other path, you have the opposite effect. So the two stages, basically, if I look at it, the two stages, NMOS is pulling the voltage. If the PMOS is driving, the PMOS is pulling the voltage up, and then it is followed by the NMOS state, which is again bringing the voltage down. So net shift, if I say VGS shift, which is VT plus V overdrive. So both of them, if I assume that the VTs are similar value, V overdrive are similar value, then for the very low voltages, the PMOS is first shifting it up. The PMOS current drain is first shifting it up. And the second stage, this NMOS is bringing it down. Impedance at the output remains low because up and down it is still 1 upon GM. And in this case, of course, the PMOS current is not constant. It is going to vary. For example, if your voltage here is too low, the current here is increasing, the bias current will be increasing. And that may basically increase the power consumption, but it will make it more closer to an ideal buffer. So in the opposite case, when the signal over here is too high, PMOS will be turning off. Now the NMOS is on. Now this NMOS is on because NMOS gate voltage now is high. So the NMOS is going to be on. And this is going to push the voltage down. The voltage as compared to this, here it will be pushed down because it will be having a VGS drop. Now for the PMOS part, since the voltage was high, it was turned off. So this PMOS is completely off. Therefore, this voltage will be relatively high. It will turn the NMOS on. So this NMOS will be strongly on. It is not having any signal, but the NMOS is on. It is just providing the bias current. But on the other branch, the NMOS is providing the signal. It is shifting it by VT from the gate to the source of NMOS. There is a VGS shift. But now when it comes to the PMOS, once again, there will be a backward shift. It will pull it up again. Overall, it tries to cancel out the effect. So if the VGS drop of NMOS is getting cancelled by the VGS of PMOS, likewise, the VSG drop of the PMOS in the common drain is getting cancelled by the VGS of the NMOS. And then the final output is coming. And this can be used to get a relatively good swing at the same time, low output impedance. So this way you can combine the common drain stage for NMOS and PMOS inputs and then get the final output. Only issue in this case is that the bias current of the common drain stages, the NMOS, PMOS common drain stages are well controlled, but the output side, the common drain stage is not so well controlled. Here the current is going to vary as the signal varies. But the impedance point of view, it provides lower impedance and good swing also, because for the maximum as well as minimum signal levels, it is able to pass the signal. Is this clear? So this is a three stage you can say. First the common drain stage, which is basically a combination of NMOS common drain, PMOS common drain, and you have followed by that a combination stage, which is merging the outputs of the two stages. And then, in case for the voltages where both are on, say the NMOS is also on, PMOS is also on, when both the stages are working, in that case, you get overall AC signal coming from this also, from this also. And as a result, both of them work as common drains. In that case, you can take a superposition, and effectively the output will still be, giving you the voltage follower operation. For the extreme cases, one of them will be off. For very high voltages at the output, the PMOS will be off. For the very low voltages at the output, the NMOS branch will be off. And intermediate voltage, both branches will be on. Is that clear?
So each path
Yes, sir.
is like each path is like two common drain amplifiers put in cascade, right?
Yes. So you can cascade it. You can say like that. Yes. So individual paths, if I look at it, it is something like cascading of common drain amplifier. Because if I just look at the independent path, you have one NMOS common drain stage followed by PMOS common drain. And then the other path is something like this path, if I look at it, this is something like PMOS common drain followed by an NMOS common drain. So it is individual path, if you look at it, is something like two complementary common drains back to back, cascading of two common drain. And then there are two parallel paths which is allowing you to handle the entire voltage swing. So once again, here for very low voltage, what will happen? Your NMOS will be off, and only the PMOS will be conducting. It will pass the signal here, but it will lead to a VSG shift. But then the NMOS will again lead to a VGS shift downward. So the PMOS, as compared to the gate, the source voltage will be higher by VSG. But when it comes to the gate of NMOS, it will again pull it down by VGS. Assuming that the VTs are close and then the overdrive voltages are small, it will have some kind of cancelling effect. Likewise, for the other path, same thing. Other path, you have this path where your signal is too high, the PMOS is turning off, and it is coming to the gate of this, it is shifting it down here, and then it is coming to the gate of PMOS, it is shifting it up back here. So the output, you have combining the outputs of these two individual common drain state. This is your NMOS common drain, and this is your PMOS common drain. And this is your output stage. This can be used, especially if you want wider swing output. And this is basically able to, in the feedback loop, ultimately now the feedback connections you will have to take in from here. But if you have to compensate the compensation point of view, if you still have problem with the compensation, we have to see where is the dominant pole. So most probably now, in case the device dimensions are large and the current that you are pumping in these stages is large, then the impedances of these stages will also be significantly less. And as a result, the dominant pole may come here only. The dominant pole compensation you may have to do here. Because it is possible that in case you have very large capacitor, then this may dominate. Suppose you are putting an off-chip capacitor, suppose the signal is driving some off-chip capacitor of very large value, picofarad value, microfarad value, then this can be the dominant pole. But if it is completely on-chip circuit and the capacitors are not that big, then most likely this will be the dominant pole, and you can compensate by putting cap here only. Is that clear? Any question before we proceed? And remember, this can be a pretty power-hungry block, because if you have to get the advantage of low impedance, you will have to burn good amount of DC current, because this impedance of these common drain stages are, and the speed of these common drain stages are also ultimately dependent upon the overall current that you push here. So especially the output stage devices, you will have to keep it big. And remember that the output stage device, there is very less control on the current. As the signal is changing, the net DC current flow in the output stage is changing. As a result, you may end up burning good amount of current. So if you keep the device sizes at the output small, then the impedance may not be that small. So there's a trade-off between output impedance and the bias current. If you want to have very low output impedance, then you have to keep these two devices also significantly bigger. As a result, their 1/GM impedances will be smaller, and that will be able to drive larger loads. but that will also require large DC current. So power consumption of the amplifier may be dominated by the buffering stage. So buffering, whenever we are doing buffering, it is expected that it will end up adding good amount of power consumption to the op amp. Is that clear? Any questions? So we can simulate this and you can try to assess the output impedance also and try to see how much it is reducing. You can also try to see that if you put a load cap, how the bandwidth changes for the unbuffered op amp and the buffered op amp. How the overall gain, there will be some reduction definitely. This overall 2 stages, the gain of the common drain is close to 1, but not exactly 1, right? So it reduces depending upon how good the GM is. If the GM is high, then the gain will be close to 1. If the GM is not so good, then there will be reduction in the gain. So it depends upon the GM of the 2 stages also. So if the bias current in the NMOS and PMOS are not very high, so in that case, the GM will be relatively lesser. And as a result, you will get comparatively lesser gain. So in that case, the 2 stages that we have here, it will lead to some degradation in the gain. It may be a factor of 0.5, it may be a factor of maybe even bigger. So there will be some significant reduction. Is that clear? Any question before we proceed further? Okay, so now let us look at some simulations, or we can cover some more topics. Let me see. Maybe we can cover comparator. So whatever we have discussed, whatever we have studied so far, it can be seen as a comparator also. It can, it can operate as a comparator as well. So the job of the comparator is to compare 2 voltages. So whatever amplifier we have built, it can also compare 2 voltages, right? So only difference is that it is going to operate in open loop. In the comparator, we don't have any closed loop feedback. We just operate them in open loop. So both the comparator, both the op amp topology that we have used can be comfortably used as a comparator. So here, if I just put this, ultimately, if you want a good comparator operation, what we need is that if you have a V in over here and you're applying a Vref over here, if the Vref is higher than V in, V out should be equal to VDD, or Vref is less than V in, V out should be equal to ground. So it is a large signal operation. So depending upon the difference between the 2 inputs, the output will be either VDD or ground. Because ultimately we are interested in the output decision depending upon V in and the Vref. Here there is no question of amplification. We are just, the output will be either 0 or VDD depending upon the relative magnitude of V in and Vref. So if I look at the transfer characteristics of the amplifier, we know that the characteristics is very sharp, right? So we have seen yesterday also, if the gain is large, this region will be very narrow. It can be 0.1 millivolt or even lower than that. If your gain is very high, 10 to the power of 4 will lead to 0.1 millivolt. If it is further high, 10 to the power of 6, 10 to the power of 5 gain, 0.01 millivolt, something like that. This transition region is very small. So this transition region, or in other words, the gain, will define the resolution of the comparator. Resolution. That means the minimum difference between the input and the reference for which it will switch completely from VDD to ground. So this level is VDD, this level is ground. So here in the comparator operation, we are not interested in this region. We are interested in this and this. So in this case, if the region is 0.1 millivolt broad, then we can say that the resolution is going to be close to 0.1 millivolt because it can resolve a 0.1 millivolt difference in VDD and ground. So a good comparator would ideally like to have as high gain as possible, but higher gain also means lower bandwidth, and that will reduce the speed at which it can work. So there will be a direct conflict between resolution and the speed of operation. So there will be, higher resolution will lead to lower speed. That is well understood. Is that clear? Any problem?
No, sir.
So apart from the resolution thing, we will also, just like we have discussed the concept of offset. So here also, because of the mismatches in the devices, we can have an offset. So what will an offset do? So for an offset, if I look at the characteristics, so here, if my ideal characteristics is something like this, that okay, if I am plotting V in versus V out. So if this is your, say, V out, and this is your V in. So when the V in is crossing, say, Vref, this is your Vref point. So below that, the V out was ground, and exactly at Vref, it became, because of the very high gain, it has a transition, sharp transition. I'm exaggerating that, but ultimately it will be very sharp. It will go to VDD. This is the ideal characteristics. But if you have an offset, what will happen depending on the negative offset, positive offset, it will shift either this way or that way. So in case of offset, it will be, shifting. So depending upon positive or negative offset, the whole characteristics will shift this way or that way. So resolution can still be high, but if the offset is there in the comparator, mismatch is there in the comparator, you will have basically, with respect to the Vref that you are applying, it will be shifted. The transition point will be shifted either left or right. Generally, in these technologies, the offsets can be as high as few tens of millivolt. So the offset can be, V offset, if I look at it, 45 nanometer, 32 nanometer. There are ways in which this offset simulation can be done. I will explain briefly. Right now in this platform, it is not available, but offset, how to estimate it in a given technology, I will briefly explain. But the general value of V offset will be, a few tens of millivolt to even 50 millivolt, something like that. So in order to reduce the offset, we have to increase the matching between the input devices. So the input differential pair is going to be critical. You need to make sure that the devices are very well matched. So there are many different, this is one of them, but the other op-amp that we have studied, remember, this current mirror load, this can also be used as a comparator. This is also used as a comparator. And here, once again, you can have offset. In order to minimize offset, once again, the input pairs, the load as well as the input pairs need to be very well matched. If they are very well matched, then the offset will be reduced. So larger W by L, larger W and L of the input devices will reduce offset, because generally the variation, the random variation that we see, that reduces with the dimension of the input devices. So for analog circuits, this kind of, matching of the devices is important. The fabrication point of view, the way we do the physical layout of the devices, we try to physically match them. The physical structure of the devices should be very well matched, so that the offset is reduced. And larger is the W and L, larger will be the, smaller will be the effect of mismatch, because the randomness reduces. Now, right now we have not studied the physical layout. So when we study the physical layout, we will see, there are ways of laying out the transistors in such a way that reduces the mismatch in the transistors, which are the matched pair. In this case, these two are matched pair. In the load pair, these two are the matched pair. Now, this is a static comparator. So these comparators are called static comparator. Why? Because these are static current. These are always having the static current. I bias. So this consume good amount of static current. So power point of view, there is a first of all, there is a significant trade-off between resolution and the speed. And second, they are static comparator. They always, keep burning the static current. There are other schemes called dynamic comparators, which are also popular. Dynamic comparator, I am drawing one circuit, which is a common one. Here, there is a latching operation which happens. These are two inverters. These two are just like inverters, cross-coupled inverters. If you have studied SRAM, you will understand. These are two inverters where the input of one is, connected to the input output of the other, and it leads to a positive feedback operation. I will discuss that. And then you have a pre-charge transistor over here, another pre-charge transistor over here. This is your pre-charge device. These are two input devices. You can have the VREF and VIN over here. And at the bottom, you have this. This is driven by clock. This is also driven by clock. So I can say, rather than putting it as a pre-charge, I can put the clock signal directly over there. So what will be the operation in this circuit? So first thing is, when the clock is low, the lower path is cut off and both the outputs are charged to VDD, right? When the clock is low, these two PMOSs will charge both the nodes to VDD. Lower side, this path is off. So there is no current flowing in the lower path. This is like open circuit. And therefore, both the outputs will be pre-charged to VDD. So that's why it's called pre-charge phase. So when the clock is low, in this case, it will be setting both the outputs. So both the outputs, I can call this, say, Vout plus, VO plus, VO minus. So VO plus as well as VO minus will be set to VDD. Now, depending upon when the clock, so in this entire duration, it will remain VDD. Now, when the clock turns high, these two transistors turn off. So you can forget about these two. Now they are off when the clock is high. And the lower transistor has turned on. Therefore, now it will start sinking current. It will start sinking current. Which branch will have more current? Depending upon which one is bigger, whether Vin is bigger or Vref is bigger. Depending upon which one of these two is bigger, you will have a positive or a bigger current in that branch. So it depends upon the input devices. If the device size is also bigger, GM is bigger, it will be able to convert that small difference in the Vin to a delta I. So it is going to be, suppose this is I, suppose this is going to be I plus delta I. This will happen when the Vin is less than Vref, or Vref is bigger than Vin. Then you will have an additional I plus delta I flowing in the Vref branch and lesser current flowing in the Vin branch. Now, what is the effect of these two cross-coupled inverters? So when this current is flowing in this inverter, initially both the voltage will try to go down because now both this lower device is turned on and it has started sinking current. So both the voltage will try to go down. But which one will go down faster? The one which has larger current. So VO plus will go down steeper than VO minus, because VO plus in this case is is basically sinking more current. So the VREF branch, because the VREF is bigger and it is sinking more current, the VO plus will go down faster than VO minus. Is that understandable? Yes, hello?
Yes, yes, sir.
And now what is the effect of that? So this now means that there is a positive feedback here. The VO plus going down faster will make this VO minus weaker, right? So sorry, the NMOS over here will make it weaker because this voltage is going down faster. This voltage is going down faster. As a result, the NMOS transistor here will become weaker, right? If that becomes weaker, then again this current will further reduce, right? So whatever it was sinking, it will further reduce. As a result, this will become slower. This will further become steeper. And eventually, because of this feedback effect, this will completely be pulled down, whereas this one will go up and become VDD. So after the evaluation period is over, we will see that one of the output will be completely settled to ground, whereas the other output will be back to VDD after this initial small glitch. So this is the positive feedback action, because depending upon the initial condition, depending upon the initial VREF and VIN status, one of the branches is sinking slightly more current, and that slight more current is leading to a positive feedback effect because bigger current here leads to faster pull down of that node. That node in turn, if this is being pulled down faster, it will make the NMOS on the other side weaker. Therefore, the current in the other branch will further reduce. And if this further reduces, this will be further, speeding up, while this will be slowing down. And as a result, this will be going up faster. This will be going down faster. NMOS will be completely turning off. Whereas the other side, the PMOS is picking up because this is becoming lower and lower. PMOS is picking up and it is going to keep it charged to VDD. So this feedback action leads to latching effect. This is called latching because depending on initial condition, these cross-coupled inverters are leading to a latching operation, and the output are getting settled to high or low value. So in this circuit, the advantage is that you do not have a static power consumption because it is clock driven. So only initially it is pre-charged, both the nodes are pre-charged. And then when the clock comes, there is, for the small duration, during the transition period, there will be some current flow. But after the current has flown, after one of them has become VDD, another one has become ground, there is no further current flow. Why? Suppose finally the output of this settles to, VDD, and this goes to ground. After that, what will happen? The lower path is still on. This clock is still on. But if one of the output is VDD, it is going to turn off the PMOS of the other side. And if this is 0, it is going to turn off the NMOS of the other side. As a result, because of the inverter action, both the branches are off. There is no direct current flow across the inverter after the outputs have settled to VDD or ground. So therefore, after these initial transition, rest of the time, there will be no current flow. Is that also clear?
Yes, sir.
So that's why this is called dynamic comparator. It is not having a static current path. This is having a dynamic operation. This is pre-charge to VDD and again then discharge. And it can operate with higher speed also. So what we have seen is in advanced nodes, we may be able to work as high as 1 gigahertz or 2 gigahertz clock. So even in 65 nanometer, easily with 1 gigahertz clock it works, provided you size it properly. So in this case, if you want to get a good operation, you need to have these two devices bigger because these are providing the conversion, transconductance operation. The small signal current difference is generated by these two devices. So these two be very well matched, and these should be slightly bigger. These two devices are just for pre-charging. The output can be small. They don't matter much. The inverters also should be well matched and they can be moderate size. But the input devices have to be slightly bigger and bigger GM has to be there. Clock stride, this device, if you make it bigger, it will lead to faster operation, definitely, but more power consumption also, because ultimately the net transient current that flows during this transition period, it depends on the clock, this bottom transistor dimension. So these points we should, the size of this one will decide the average current flow. This size will decide the GM and hence the resolution. Because if the GM is better, it will be able to resolve better and resolution. Because a small difference in voltage, if you have to convert it into significant difference in the current, you need to have good GM. So you need to have good GM for these transistors. So now people generally, in order to improve the resolution further, people do a pre-amplifier. So add a pre-amplifier. So first there can be an pre-amplifier stage. It can be any nominal pre-amplifier. We don't need a very big gain, but the purpose of pre-amplifier is to enhance the signal difference before it goes to the latching comparator. So first we can feed the signal to this circuit V plus or V in, V ref, and then let this output go to the comparator. This goes to the comparator. The advantage of this is that it will improve the resolution, because here whatever difference is coming between V in and V ref, you are enhancing it a little bit. So as compared to the original case, here your difference has been enhanced. And then this enhanced signal is going to go to the next stage. Is that clear? So generally, this will be accompanied by this is the clock driven dynamic comparator. And before that, you will have a pre-amplifier stage. Pre-amplifier stage, if you use it, it will be static. That will be consuming good amount of static current. Just a minute. What is this? किस चीज का है?
इसका क्या क्या है देखिए सर.
ये आप कौन दिया करने के लिए अभी?
ऑफिस में दिया, सॉफ्टवेयर का साइन सिग्नेचर लिया है ना.
मैं एक बार उनको मैं बात करता हूँ.
मैं तो सर बात कर लीजिए.
बात करता हूँ, एक मिनट मैं कर दूंगा आपके थोड़ी देर. तो yes, so the thing is, in this case, the moment you're using a pre-amplifier, advantage is that you are able to amplify the difference. You are able to, amplify the signal, and as a result, the effective resolution goes up. But the bad point is that it will definitely have some static power. So it does not require very high gain, because the purpose is just to amplify the difference between the two levels. Now, what will be if you use the pre-amplifier, even if we don't use it, so what will be the voltage range for which it will be able to work? So does this comparator work for all signal levels 0 to VDD? Where it will have problem? Yes, you guys are listening?
Yes, sir.
So this comparator that I have shown, this latch-based dynamic comparator, will it work for all values of voltage? It's simple, right? What is the problem? It is an NMOS input device. So what was the problem? Till what point will it work?
So the
So
NMOS
it will
must be
not
on.
work beyond
Yes, hello?
Then the NMOS must be on, right, for to work. And
Yes.
also the lower mode.
Yes, so till what voltage it will work?
Sir, it will work greater than the voltage of greater than this the drain voltage of the lower NMOS plus VTH.
Yes, so basically now this is not a saturation region current source. This is acting like a switch turning on and off. So mostly it will be the VGS. So it will require at least some VGS drop. So it will be higher than VT. So VT is 0.3 volts, then it will not work below 0.3 volt, or it will be working erroneously. So and likewise, upper side, you can have just the flipped version of this, right? So you can also have the PMOS version where the input device is PMOS, right? So that will work from 0 to the VDD 2. Sorry, the maximum value that it will work is VDD minus VT, mod VT. So just like I have drawn input devices as NMOS, I can just reverse the whole thing. I can make the these three devices PMOS version, right? In that case, the NMOS, this inverter, etc., will come down. It will be the alternate version. Are you getting the point? There can be an alternate
sir.
version of this where you can have, say, the PMOS device will come at the top, then you have two PMOS devices at the input.
And basically, this will be like a pull-up device, right? And that was a sort of pull-down.
There is no pull up or pull down. This is a PMOS input device comparator, and you are going to have an NMOS input device comparator over here. Sorry. In this case, this comparator, what will it do? This will be CLK, CLK. So when the CLK, in this case, when CLK comes, you can put the CLK bar also, and then you can put this as CLK bar, so that when CLK bar comes, that means CLK is high, then it will be evaluating, and CLK is low, then it will be pre-charging. Same thing. But in this case, the difference is that in the earlier case, the input devices were NMOS, and lower side, upper side, it was pre-charged to VDD. In this case, this will be discharged to ground, and then it will be conditionally coming up depending upon V in and Vref. This is the complementary version. So this will work nicely up to certain voltages, which is VDD up to VDD minus mod VTP. Other guy will work from 0 to VDD to VDD to VTN. So remember that this is a latch-based amplifier, and we are not worried about the saturation region condition so much. But definitely the overall resolution of this comparator does get affected by the DC level. So if the DC level is towards mid value, that means the V in, Vref, etc. towards the mid value, then the resolution generally is found to be bigger or better. That means it will be able to resolve a smaller difference because the transistors are closer in saturation region. But if the input signals are much higher towards VDD, it will operate. But remember that this too will be in triode region in that case. So in that case, the GM, etc. will be lesser. So if your signal is very close to VDD, very high, then the transconductance of these input devices may be reduced, and that will lead to poorer resolution. So resolution of the comparator in this case will not remain very good all throughout. The resolution will change as a function of the DC levels, whatever is the DC level of Vref and V. For the DC level going below VTN, definitely will turn off. There is no problem, no doubt about that. But for input and reference level both going very close to VDD, these two devices will be in deep triode region because the gate voltages are too high. And as a result, GM will be lesser, the delta I that we produce will be lesser. That will also lead to reduction in the resolution. That means the difference in the VREF Vin that it can resolve. So the comparator resolution will be dependent upon the DC level. But in order to make the comparator full swing, you can always, you can you have to apply the preamplifier for the two cases. So in this case, the preamplifier will be this one. If you have to go for a preamplifier for this, you can appropriately choose. It can be because here this is suitable for voltage signals going all the way to say this can work all the way to ground, and it cannot work from VDD to VDD minus mod VTP. So for this one, we can choose an NMOS, the differential pair, which is just the reverse version of this. Right now, this one, the signal that will produce here, this can go all the way to say VDD minus VTN. So the output signal max value can be something like this. Min value, it will be V in minus VT, something like that. So here you can get some amplification. After amplification, this signal, because it is anyway creating a difference, and the signal, the maximum value of this comparator, sorry, this preamplifier will be going to VDD minus VTN. Minimum value, it can, if the signal difference is very large, it can go down, close to VDD also. Like suppose the signal difference is very large, and this is 1 volt and this is 0.6 volt, something like that. So in that case, the difference can be big. And in that case, actually preamplification is not required. Preamplification is helpful only when the signal is very close. So now in any condition, your signal can become very close to the reference. And for that case, in order to resolve this properly, we need the preamplifier. So if the differences are already big, then preamplifier is not playing much role. It can have one of the input already very high, other outputs already very low. Then it's not very significant. But when the difference is small, the two signals are close, then the preamplifier roles come into picture. And in this scenario, as I said, by default, the maximum value over here that you are going to get is going to be, depending upon VDD minus VTN. Minimum it will go from V minus, VT. It can go further lower if the difference is bigger. But again, the preamplifier also here will work for what kind of levels. So the signal here will work for V in, which is VREF, which is higher than VT. So if the VREF in your application is fixed, you know that the VREF is always, suppose VDD by 2, or VREF is always a fixed value, suppose 0.7 volt. So in that case, I can use this. There is no problem because the VREF is getting fixed. And then after that, the signal produced at the output will be fed to the next stage. But in applications like ADC, etc., the VREF also varies. The VREF keeps changing from 0 to VDD dynamically. So if that kind of application is there, where the VREF itself is changing from 0 to VDD, this single preamplifier may not be able to work because it will work only for certain ranges of VREF. So VREF from 0 to VTN, it will not work. So then I have to take help of the another preamplifier stage, which is PMOS differential pair. So I will reverse this and I will go for a PMOS differential pair. Something like this. In that case, this will be your output and this will go to the comparator. So this stage will work for VREF all the way to 0. This stage will not work for 0 VREF. Likewise, this stage will work for VREF all the way close to VDD also, whereas this stage will not work for VREF close to VDD. So depending on application, in case we need the full swing, in case the VREF is also changing and we need to cater for the entire range of VREF, then we need to combine both these, the first and the second, the PMOS differential pair as well as NMOS differential pair. Followed by that, you can have the comparator stage, but you can use the output of one of them. To decide that, you can have a fixed comparator. There will be a fixed comparator where you're going to compare with VDD by 2. The input you first compare with VDD by 2 and decide where the signal is, whether it is higher than VDD by 2 or lower than VDD by 2. And then based on that, you can decide, or depending on the VREF also, you can decide. So in order to get the full range, we can have a combination of these two stages, and then based on the VDD by 2 comparator, we can decide which part to use. So in many applications, especially ADCs, etc., you will make use of this kind of comparator. And likewise, there are, apart from ADCs, there are several other applications where comparators are used. In power management circuits also comparators are used. So both the static comparator as well as dynamic comparator, you should be aware. And these are simple circuits. So the static comparator is simply, whatever you have done, you already done the static comparator. Only thing is you can simulate it as a comparator, put a reference voltage in the terminal, see the resolution, and try to get the characteristics. Like ultimately it depends upon the gain. If the gain is high, this transition will be very fast. But for comparator, the speed is very important. And for example, if you're going for 10-bit ADC, what is the resolution we are targeting? We already discussed
1024 bit, right? So 1024 bits, so at resolution of 0.001, 0.1% resolution.
0.1 millivolt, because VDD is, if I assuming that close to 1.2 volt or 1 volt, and your 10-bit resolution means 10, you are having 1K value, right? So you're dividing the entire range into 1K. So that 1K, we need to have 1 millivolt on resolution. So it should be able to resolve less than 1 millivolt difference. So we will need the transition region to be a fraction of millivolt, right? So the gain should be greater than 10 to the power of 4, between 10 to the power of 3 to 10 to the power of 4. So again, it depends upon the application. So in the ADC, you are using this comparator in ADC where the resolution is very high. You are going for 10-bit resolution. then accordingly this transition region should be very sharp. You need to have large gain because there you are trying to resolve very small differences. You are trying to resolve 1 millivolt differences. So this transition region must be sharper than 1 millivolt. If you're going for higher, if you're going for higher resolution ADC further higher, then accordingly it has to be enhanced. So whatever preamplifier you put, whatever is the gain of the preamplifier, suppose you are having a gain of 4 or gain of 8 in the preamplifier. By that much, the resolution will be effectively increased because you are amplifying the difference by that much factor. Is that clear? So just like op-amp, comparator is also a very important part. Many such applications, many circuits, you will find comparators being used. Any question? Okay, if you don't have any question, we can quickly go to some of your simulation. So let me stop recording. Otherwise, again, anyway, it will become very big. So is it being recorded? Why this thing is not coming from this? Okay, so it can go back to this one. And I can stop recording. Yes, so